Okay, let's go and start the class. If you recall, last week we talked about the Magnus effect, essentially how a rotating cylinder will transform a non-lifting flow to a lifting flow, where we have the generation of lift. And I showed you a YouTube video to help you visualize and understand the effect a little more. And I told you if whoever like builds a Magnus device in quotation will get 2 bonus points. We only had one like video recording submission from John Scherger, right? Thank you. And I just want to show the video, and afterwards he can just elaborate on what he did a little bit. You can see the effect of lift here. See, it goes up because of the lift and then comes down. Do you have anything to add?
The same thing that they did in the video with the rubber bands and just cut it around. It took a while to get a good shot of it because a lot of times it just kept not working, but after like 30 minutes I finally got that to work. So.
Okay. Yeah, thank you for doing this. And yeah, so he got 2 bonus points. I guess hopefully he had fun a little bit. And let me thank you again. So today we are going to finish the discussion on chapter 3 and hopefully move on to chapter 4 for next lecture. I have already uploaded an ANSYS tutorial on YouTube on the same channel. So if you're a graduate student who wants to do their project using ANSYS or ANSYS Fluent, you can watch the tutorial. It's roughly around an hour, but I'm pretty sure you can skip forward. It shouldn't take you a long time to figure out what to do. But and your mid-semester report is due on March 24th, I think. So 24th. You have to have some results, some preliminary results. You have to show me you have done something, unless we are in communication. There is one group that I'm talking to, and they're waiting for the wind tunnel to become available, essentially, to get installed and become ready to use. They definitely get more time to work on the project, but otherwise, you have to submit your midway report by March 24th. Do you have any questions? There was one undergraduate student who approached me last week about possibly doing the project. I don't remember who he was, but if you are still interested, you have to start working on the project sooner than later. Okay, so to sum up, ANSYS tutorial is uploaded. I will upload that Python tutorial that I mentioned pretty soon. I have updated the homework as well. I've added 2 problems to the homework. You don't need to do any programming to solve those problems. You just have to understand the finite difference methodology as well as the thing that we are going to talk about today. Today, we are going to talk about source panel method. This is the second lecture on the numerical simulation lectures. Let's call it numerical simulation, numerical aerodynamics. Okay. So in this chapter, what we were mainly focused on was to understand the elementary flows and how the combinations of those elementary flows work with each other, the concept of Laplace equations and the solutions to those Laplace equations. And essentially, we combined a couple of elementary flows to build specifically two more complex flows, and then find the velocity profile when it comes to those flows. But what will happen when your geometry is not just a simple cylinder? It's something like this. How would you analyze a flow like this? Can we use the elementary flow we have already talked about? In principle, yes, we can, right? Because we don't have any limitation. As long as you are in the inviscid incompressible aerodynamic regime, you should be able to use the elementary flows or potential flow theory to analyze this airfoil. But how can we break this down, the flow over this airfoil? How can we break this flow down to a simpler elementary flow? That's where the problem comes in. It is going to be harder for us to get a very good understanding of what are the elementary flows that combine with each other to build this more complex flow. That's when we try to come up with a numerical approach to make it easier for ourselves, essentially. And that's where the source panel methodology, as far as I'm aware, this was the first methodology that helps understand or analyze the aerodynamics of the flow, right? To find the pressure distribution over an airfoil or a cylinder, or these type of things, right? To feed the code to the computer and ask the computer to do the analysis for us. So, and this is a series, this is the first of a lot of panel methods that we are going to discuss. Well, what does this part, the panel method part, refer to? This essentially refers to the fact that we are going to break up this airfoil to small panels, or any airfoil for that matter. If you think about it, it looks very similar to the finite difference methodology. We are essentially linearizing this geometry, right? Dividing it up to different point sections, to different grid sizes. So the very similar idea to the finite difference methodology, but it's a little different. And this method has been in use since the 60s. Nowadays, no one really uses this method for a very industrial analysis. If you go to the industry, there are software that use this method, but no one writes a code using this approach, right? People usually use the family of finite difference, and finite volume, and finite element method that we have talked about. So, panel method divides your system, your geometry, to different panels. But what does this source panel method mean? Source at the beginning. This essentially means that we are going to use the concept of source flow to solve the problem here. So, how can we do that? Let's go back to an earlier discussion we had. We added a potential flow, a uniform flow, plus a source flow to build this type of more complex flow. If you recall, we had a whole discussion about it and how this flow works. We essentially are going to use the same idea and principle to transform that flow to flow over an airfoil. How are we going to do that? The first step is to understand what is a line source. So this elementary flow that we have talked about so far is a point source. We want to extend this to become a line source. So instead of having one point as your source of the flow, we are going to have a line as the source of the flow, which essentially works like this, right? We are going to extrude this point, right, to give it some length. That's the idea. So this is a line source compared to a point source. And if you put these line sources beside each other, I'm just gonna give you the side view of it. Something like this. We are going to have something called the source sheet. This refers to the fact that this line source, this sheet is made up of a lot of line sources. Does this make sense? Just to the finish, right? Okay. But the tough part that's a little harder to visualize. Let's say you have this source sheet, and I'm not gonna. We have line sources all over. Okay, it goes from A to B. We want to find the velocity potential that this line source induces at this point P. Velocity potential induced at P. To understand what this means better, let's go back to a regular point source. With a strength lambda. What is the velocity induced by this source at this point P? What is the velocity potential? Who can tell me that? And the strength of this source is lambda. What is it? Go back to your notes. And tell me what the induced velocity potential at point P is.
You want the velocity potential?
Yeah, induced velocity.
It's that triangle thing, lambda, so it is.
Okay.
Times the natural log of r.
Okay.
Over 2 pi.
Exactly. So the velocity induced by this point source at point P is the strength of the source divided by 2 pi multiplied by natural log of the vector r that connects your point source to point P. Velocity induced by this point source at point P. Okay. So we want to find the velocity induced by this source sheet, and this is the letter lambda. That's the capital letter lambda, and this is the small letter lambda. Okay, lambda, not lambda. Okay, so we understand this part. We have seen this part before, but here we want to find the velocity induced at point P by this source sheet, which is a combination of line sources, right? Which are extensions of point sources. Okay. So to find that, we just have to take a very small LAS. Yeah, sure. Let me see if we have any yellow chart. Yeah. This should be. Sure. Okay. So we want to find the velocity induced at point P, the velocity potential. So we want to find the phi is induced at point P by this force, by this source sheet. We take a very small element of this line with the length ds, and we are going to assume that the strength of each source on this line is a small lambda, which is a function of s. So a small lambda is going to change with respect to s. So what is the strength of this small element? What is the source strength of this small element ds? It's lambda multiplied by ds. Does it make sense? So it's essentially, it's a couple of unknown number of sources that are going to be inside this ds, and their strength is going to be lambda multiplied by the length of that ds. So what will be the velocity potential induced at P by this small section of the source sheet? It's going to be your strength of that small section of the source sheet divided by 2 pi, right? Multiplied by the natural log of the distance from that source sheet. Okay. Does this make sense? So we are going to call that velocity potential d of phi, and it is going to be equal to lambda ds divided by 2 pi natural log of r. Okay. Just have to keep in mind that this r is just a vector, a function of x in Cartesian coordinate system, and y, right? And its magnitude is a square root of x squared plus y squared. Okay. So, yes. This is not lambda times s. This is lambda, which is a function of s, like f of s, which essentially means that lambda is changing as you move on this line. May change, right? Okay. So what would be the velocity potential at this point P induced by all of these source sheets? What should we do to find that? Exactly. We just take the integral of d of phi from A to B, right? That's it. So your phi, which is a function of r, which essentially means that it is a function of x and y, is going to be equal to the integral A to B of lambda ds 2 pi natural log of r. Okay. As long as you can, so as long as you can define a source sheet that can resemble the shape of this airfoil, you should be able to calculate that integral, right? But the idea here is that we cannot find this type of source sheet, right? We want to make it simpler, right? So we are going to divide, I'm going to draw this again here. We are going to divide our system to different panels. Okay. And then we are going to, and these are all line sources, all of these panels. The difference here between this source sheet and these panels is that the strength of your source is going to stay the same throughout one panel, okay? So essentially we are dealing with, instead of dealing with infinite number of sources, line sources, we are only dealing with 1, 2, 3, 4, 5, 6, 7, 8 sources, right? It's just simpler. You are going to lose some accuracy, but it is simpler. So how can we calculate the velocity potential that is induced by these sources onto this point P? Okay, how can we do that? Here, we are dealing with d of phi, the derivative of phi, small element of phi. But now that we have moved on to panels, we are going to deal with delta phi, okay? Which is going to be equal to lambda of each panel, lambda of j. These panels are 1, 2, 3, 4, 5, 6 up until j, divided by 2 pi. Then integral of natural log of r pj, and I'm going to explain what this is, ds of j. Okay, so what do we have here? Again, the idea was you are dealing with finite number of panels instead of infinite number of line sources, right? So we are going to have finite number of lambdas, lambda 1, lambda 2, lambda 3, lambda 4, 5, 6, 7, until lambda j. For one panel, we can take we are looking at only one panel here, right? The velocity potential, this one panel induces at point P. This lambda is not going to be a function of S because that was the definition. Lambda is going to stay constant on one panel. So we can take it out. And it's going to be lambda of j, which tells us that this is lambda of that specific panel, okay? And 2 pi is also constant. And then for the rest of it, we are taking the integral of natural log of rpj, which is a distance between this panel and this point. This is r of pj multiplied by ds of this panel, this ds, right? Which is a function of x and y in Cartesian coordinate systems, of course. So, is there any questions here? We are moving from the integral to the panel method, to series essentially. Okay.
Are all the panels going to be the same distance?
No, not necessarily. They can have different distances. Okay. So based on this, how can we find phi? We have delta phi, which is going to be give us the velocity potential induced at this point by one panel, but we want to find the velocity potential induced at this point by all of the panels. What can we do? we essentially have to calculate this for each panel. J equals to 1, J equals to 2, J equals to 3, 4, 5, 6, and then add them up, right? What does this remind you of? Someone says something, series, right? Someone says series, which is correct. So essentially, you are going to get J equals to 1, sigma of J equals to 1 until n, which is the number of your panels, delta phi J. This is equals to sigma J equals to 1 to n lambda of J 2 pi A to B natural log of R Pj ds J. So velocity induced by these panels on point P. But if you recall from this analysis that we had, the flow here, and with the source inside, right? You're really interested about what is happening on the surface of the airfoil, right? Or on these panels, right? How much velocity potential induced by, for example, these other panels on this one. So we want to move the point P on the panels themselves. And all of these panels are represented by a control point that is in the middle of them. Does this make sense? Yes. Okay. That's a good question. So here, the idea was lambda is changing with your ds, right? But what we have done is to replace these lines with different panels. What is the main point of these panels? The main point is lambda is going to be constant throughout the panel. So we have lambda 2, lambda 3, lambda 4. So the velocity induced by this panel on this point P is going to be lambda 4 divided by 2 pi, and lambda 4 is not changing, it's constant. You can take it out of the integral. Integral from this to this, so that these actually change as well. This point to this point of natural log of r, this distance, right? ds multiplied by ds, which is the derivative of the surface here. Okay? So do we have any other questions? Okay. So we have the velocity potential induced by panels, a couple of panels, on a point P that is not necessarily on the panels themselves. But the next step, since we only care about that surface and what's happening to the surface of the airfoil, because we want to mimic the surface of an airfoil, right, in our flow analysis. We want to find the velocity induced by, let's say, this panel on the other panel that is here. So your R, instead of being RPJ, is going to be R of the velocity potential induced by J on I. So it's going to be R of IJ. Right? That's the distance between the two center points of the panels. Does it make sense? Velocity potential induced by this panel on this panel. Does it make sense? Okay. So how would our series here, how would our equation change here? The only thing that has really changed is going to be your R. So your phi is going to be equal to sigma j equals to 1 to n lambda of j 2 pi integral of a to b r, instead of pj we're going to get rj dsj. That's the velocity induced. That's the velocity potential induced on panel I by panel J, right? This panel I can be here, can be here, can be anywhere. Okay. Is there any questions so far? That's the velocity potential induced by one panel J to the panel I. Okay, and since we are taking the sigma, this is essentially going to mean that this is the velocity potential induced by all panels on one of the panels. Okay, on one panel I. If you have any, if you're confused or if you have a hard time understanding this, please stop me. Yes. Two random panels, so it can be any two panels, right? And we are here, we are not moving on panel I. So essentially what we have done, let's go back to this line here. No, it's just a number of panels. So panels can be I and J, both of them. This can be I equals to 1 is going to be this. 2, 3, 4, right? When you keep the I as 1, let's say I is equals to 1, just to make it easier to understand. Your phi is going to be equal to sigma, j equals to 1 to n, lambda of j, 2 pi, integral of, this is not a to b, integral of r 1j dsj. Okay? So we keep I as 1. That's your first step. Then j is going to change from 1 to 4, right? So phi, that is induced by 1 on 1, is going to be lambda 1, 2 pi, integral of r11 ds1. Okay? Then phi induced by 2 on 1 is going to be lambda 2, induced on this one, 2 pi, integral of r12 ds2. Phi induced by 3 on 1, lambda 3, 2 pi, integral of r13 ds3. And then phi induced by 4 on 1, lambda 4, 2 pi. Okay? So this is what this equation means. Right? We are, if you keep I as 1, we are going to find all of these phi's velocity potential that are induced at this panel 1 by these other panels and also itself. Okay? And we will talk about the velocity induced on a panel by itself later. Because this value is going to be 0, right? There's no distance between the center of panel and itself. Right? Just to make sure that we are on the same board, this R is again a function of X and Y, which is going to, let's say, R of Ij, the distance between panel I and panel J is going to be X of I minus X of J, I plus Y of I, Y of J, J. And don't confuse these unit vectors with I and J. Yes.
I have more of an abstract question. I understand like the process of it, but from reading the intro of this section, it says it's for non-lifting flows.
That's right.
how can that flow over an airfoil be non-lifting? Like, what's the point of analyzing a non-lifting flow over that airfoil?
Use pressure distribution. Pressure distribution is an important factor, right? You want to find the pressure distribution. But so this methodology is a very general methodology. Applying a source line or line sources to it will make your analysis non-lifting analysis. But in the next chapters, we are going to apply vortex flow to it, which will make it flow like lifting. Okay. And we will talk about that later. Okay. So are we clear here? And then this phi, the velocity potential induced by all of these panels on this self is going to be just the additions of all these four. Okay? Is this clear? Okay, then you can do the same thing. You can set I to 2 and then move J from 1, then 2, 3, 4. Then you can make your I3, which is this panel, the velocity induced by this one, plus the velocity potential induced by this one, velocity potential induced by 3 on itself, velocity potential induced by 4 on 3, right? Yes. That will be, so this is phi of ij, right? We only did phi of 1j. We will talk about it, we'll get that, okay? So just hold on to this phi of 1j. Velocity induced by all of the panels on one point, okay? Okay. But how would this help us create a more complex geometry? How would this panel theory method is going to help us? It all goes back to the velocity field that is on here, right? Let's go back to this airfoil. We have V infinity. Okay. What is the velocity field in this direction, or V normal? Just regular flow. Forget about the panel theory. What would be the velocity field in this direction? In the normal direction. Velocity on the wall in the normal direction. Is going to be 0, right? Velocity normal to a wall is going to be 0. If you don't have any suction or any like blowing of the wall, velocity normal to a wall is going to be 0 at the wall itself, okay? What about the velocity tangent to the wall? That one, in the inviscid incompressible flow, what did we say about the velocity of that one? We actually will get there. Let's just work with the velocity Vn. Okay, so here, velocity Vn, we are going to have two velocities here. One is going to be one component of V infinity, okay? And the other one is the velocity induced at each point by these sources that we are going to replace the airfoil, right? So two velocities. Component of V infinity, since the velocity, the total velocity has to be 0, component of V infinity that is normal to the wall, plus whatever this normal velocity that is coming out of the sources that we are using is, I'm going to call it VNS, right? normal velocity due to the source panels. This has to be equal to 0, right? Because the total velocity, total normal velocity on a wall has to be 0. So, okay, we are moving one step closer to a final solution. Let's say you have these panels here, and the angle your flow direction makes with a panel is called angle beta. So your free stream velocity, normal component of free stream velocity is going to be V infinity sine of beta. This angle is also going to change for different panels, right? The angle this makes is going to be different than the angle this one makes with your free stream flow. Sorry, this is cosine of beta. Okay. Is this clear? Yes. V infinity, no. Which one is V? This is normal component of V infinity. That's normal to your panel. So come back here. V infinity. You want to find the component of V infinity in this direction. Okay? So V infinity cosine of beta. And then has to be plus V of NS. What is this velocity? How can we calculate this velocity using the velocity potential for each panel? We have the velocity potential for one panel here, panel I. Okay. How can we calculate the normal component of velocity in that direction? Exactly. So this Vn and S, and this N is normal, S referred to the source panel, is going to be your partial of phi for that specific panel, panel I, and the potential that is induced on panel I, but by all of the other panels, divided by take the derivative of that velocity potential with respect to N. Okay? That's it. That was the idea of the velocity potential. If you have the velocity potential, to find the velocity in any direction, you have to take the derivative with respect that the derivative of velocity potential with respect to that direction, right? For a stream function, it was a little different, right? For velocity potential, it was a little more straightforward. Okay, so let's take that derivative then. Yes. That's what do you mean by regular Vn? It was I just wanted to showcase the velocity normal to the panel, right? It was a direction of normal to the panel. That was the idea, right? You're gonna have two components of velocity there, velocity induced by all the other panels, on this, and the velocity, the normal component of V infinity. Okay? Okay. I just caught one mistake here. These are all natural log. So if you don't have natural log in your analysis, this is our natural log of R, right? I'm sorry that I didn't catch this sooner. So this Vn and S, velocity induced by the sources, is going to be the derivative with respect to N of sigma j equals to 1 to N lambda of the J 2 pi integral of natural log of R Ij dsj. Okay, the only thing that is really changing with respect to n here is going to be your natural log of r. So we can take the rest of it out of the derivative. And if you recall, we had a component here, which was this one, the velocity potential induced on a panel by itself. We just simply are going to use lambda of that panel, which is going to be lambda of I. I'm going to add it in front here, divided by 2 for the velocity induced on a panel by itself. So this phi, that phi over there, is only going to include these 3 if you only have 4 panels. Okay, so this is going to be your component of velocity, your normal component of velocity induced by the velocity potential on one panel. And then we have the free stream velocity, normal component of free stream velocity. Just add them up all together. And it has to be equal to 0. This is a linear equation, right? That's a sigma, but we have the unknown here, like R's and everything are by design. You choose the panels. You choose the number of the panels, you choose the directions when you're doing the simulation, you're doing the programming. The only thing you really don't know here is the lambdas, is the strength of the panels, right? So for this one, we have one equation, but we have lambda j, like sigma lambda j. We have lambda of all the panels. If you have 4 panels, we have 4 lambdas. So we have one equation and 4 unknowns. What should we do? What should we do? What's the solution to this problem? You essentially have to apply the same equation here to all panels. This was only applied to panel I, right? Which is panel 1. Then you write the same equation for panel 2, panel 3, panel 4, right? Panel, how many panels you have? Doesn't matter. Like panel 100. And then you will have a system of, let's say you have 100 panels. You will have a system of 100 panels and 100 equations, 100 equations and 100 unknowns, which will give you the final results of, and which will give you the final strength of the panel, each panel, right? A strength of the source for each panel. And I assume you should know how to like solve a system of linear equations, unknowns, and like the same number of unknowns. Usually, we have a lot of different methods, right? And you have seen them in your numerical methods course, hopefully. Yes.
So the point of all this is so that we can find lambda. That's the actual goal of setting up these equations, to figure out lambda for each panel.
That your eventual. So that's a good question. The goal of this equation is going to find lambda, right? What will happen when you find lambda? You will be able to find the velocity on the geometry. How would you do that? We said the normal component of velocity is 0, right? But the tangential component of velocity is not 0, right? So how would you find the tangential component of velocity? You essentially calculate the lambdas first using this boundary condition we have for the normal component of velocities. And then you find the tangential component of velocity, and I'm going to use V of Vs and S. Maybe I should have used different words, but S and S, which is the velocity induced by each panel in this direction, while other panels on this panel is in this direction, not in the normal direction, in the tangential direction, right? By sources. So let me use TNS. Tangential induced by source, right? To find those. And how would you calculate that? You have the potential. You take the derivative of potential with respect to your S or T, right? Let's actually keep it to S because we have always used S here. Velocity tangential to the surface, right? And you can just go through the whatever we had. Just have to take the sigma j equals to 1 to n lambda j over 2 pi integral of partial s natural log of rij ds. Okay, and this part, this integral is named I of ij. So you find the lambda through this system of equations and unknowns, just linear algebraic equations, and then you find the velocity that is tangential to your panel. That was the idea of the inviscid incompressible flow. You only have tangential velocity, right? Okay. And when you find this tangential velocity, you just have to add this to this Vs and S to V infinity tangential component of free stream velocity, sine of beta r. That was the angle between the flight path and the panel to get the velocity of each panel. So eventually we have the velocity of one panel, okay? And you do the analysis for all the panels, you have the velocity for all panels. What is the next step? Next step is to find the pressure distribution for each panel on each panel, 1 minus Vi divided by V infinity squared. See, a very simple methodology. Very simple. Yeah. Yeah, actually, one of your, as I said, one of your homework problems is you have to use this methodology to solve one of your homework problems. Based on the enthusiasm, I assume we can include it in your exam as well. But, okay, is there any questions? No. Did we all follow what happened? Okay. So. As long as you show the equations you have used and like use your MATLAB, you include your MATLAB code, yeah. Yeah, definitely. That like yes. Partial pressure. No, the final goal is to find the pressure coefficient for each panel, right? When you have the pressure coefficient on each panel, you essentially have the pressure. You have the pressure coefficient here, pressure coefficient here, 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 here. You have the pressure distribution, right? If you can. When you have the pressure distribution, you can calculate lift and drag, right? You know, what was the equation? CP upper minus CP lower, dx and dy, right? The integral of that, right? Each of what? No, there's no other summation. Your goal here is to find the CP, right? When you have the CP, let's say you have the value of CP here. Here you have the CP1. CP is like 2.5. CP is 3. CPO is 4. CP is 5. CP is 7. And CP is 8. When you have the distribution, you can use the equations we already have. Integral of CP lower, CP upper, dx to find the lift and drag coefficient. Okay, let's solve an example to better understand this problem. Okay. One thing that John, right?
Yes.
John brought up was that this method, the source method, is used to analyze non-lifting flows. Okay. So essentially, flow over a cylinder, right? This was the thing. If we want to analyze lifting flows, we have to use a different elementary flow, which is the vortex flow. And this will be the whole topic of chapter 4, right? First, we will do analytical solution to vortex flow, vortex sheets, and all of those things. Very fun. And then we'll move on to numerical analysis. Okay. So let's solve this example. And I'm going to ask you to do this with me. Okay? We wanna apply the same methodology on a flow over a cylinder. Flow over a circular cylinder. We want to apply this method, and I want all of yours attention, please. But if you don't want to attend, I mean, you can just. Sorry, guys. Okay. So we want to apply this method that we just learned to analyze flow over a cylinder. Okay. And what you want to do, this is your homework. I've asked you to divide this cylinder to 4 panels, right? And then apply your methodology, this method, to the 4 panels. But in this example, we are going to use 8 panels. Okay? Six, 7, 8. We want to carve up the cylinder to 8 panels. As you can see, we are not analyzing a whole cylinder. We are only analyzing 8 panels that resemble a cylinder for us. Okay? So the first thing you want to do is to find this I of j, I of ij. That's the hardest part. Integral of natural log of r ij ds j. And I'm sorry, forgot about the partial derivative. Partial n. That's the first step. what you want to address here first is what is R of ij. Okay. Let's take two of these panels, two random panels. We have the center point, which is, we have the center points. Let's call this point xi and yi. This is, so this is your I panel, and we are here. We are going to have xj and yj. So essentially, we are assuming that we have the location of these two panels. These 2 points, which are the ending points of any panel, we are going to use capital X, J, and capital Y, J, capital X, J plus 1, and capital Y, J plus 1. Same idea here. The coordinates of this point, xi, yi, xi plus 1, and yi plus 1. This is your normal vector of for panel I. So this is ni. This is your normal vector for panel j, n of j. And the flow is in this direction, in this shaded direction. So this will be your beta I, and this will be beta j. Because we start, this is where you start your beta. Keep that in mind. Beta I, beta j. Okay. So what is R of ij here? How can we calculate R of ij? Any ideas? Xi minus xj, yi, thank you, yi minus yj, and square root. This should be your R of ij. That's the difference between that's the distance between the two panels. Okay, so what will be the partial n of natural log of Rij? It will be, who can tell me what is the value for this? Partial n of natural log of R. It will be the derivative of R divided by R, right? So 1 over Rij, the derivative of, or partial n of Rij, right? So are you following? Yes? Okay. So what is the derivative of Rij with respect to n? That's the derivative of a square root, right? That's a minus sign. That's the derivative of Rij is the partial derivative of a square root of whatever value we have over there. It's going to be the derivative of whatever that is inside this square root divided by 2 multiplied by that square root, right? You remember the derivative of a square root? Derivative of square root of x is dx divided by 2 square root of x, right? Plus yi minus yj. And what do we have on the numerator? The derivative of whatever here underneath here, which is going to be 2xi minus xj dxi dn plus 2yi minus yj dy I dn. Okay? And if you come here, you can see that this is going to be your dxi. This is going to be your dyi. So dxi divided by n is going to be cosine of beta, and dyi divided by n is going to be sine of beta. So we're going to get 2xi xj cosine of beta I plus 2yi minus yj sine of beta j divided by the 2 square root whatever. And here we have 1 over I rij. Rij is this. So this is going to be 1 over rij multiplied by this whole thing. So on the denominator, we are going to get these 2's will cancel out. Eventually, this value is going to be equal to xi minus xj cosine of beta I plus yi minus yj sine of beta I divided by xi minus xj squared plus yi minus yj squared. Okay, so this will only be I of j, or I of ij. That's this value inside the integral. This will be this derivative. Only this one. It will be this. Okay? Is there any questions? Yes.
You show how dxi over dni is equal to cosine of beta I, just quickly.
What is cosine of beta I? Here. It's x divided by r, right? So we just did it the other way. That's you always have to come back to this. Right? Okay. I guess let's just stop here and finish this example in the next lecture, right? But eventually, what we are gonna do is to find an equation that gives us I of ij, right? And then using that, we are going to find the velocity potential as a function of lambda induced on each panel, right? I of 1, 2 will be one number, I of 1, 3, 1, another number, I of 1, 4, I of 1, 5, I of 1, 6, all of those different numbers, right? You will have one equation with with 8 unknowns, lambdas, 8 lambdas. Then you write the same thing for panel 2, 8 equations, 1 equation, 8 unknowns, until you have 8 equations and 8 unknowns, and you can solve that system of equations. But here, your homework problem is actually easier. You have to do this for 4 panels, which makes everything much, much easier. You essentially don't have to do all of these calculations because your ds for like one of the panels is only going to be dy. For the other one is only going to be dx, right? Taking the integrals is going to be much, much easier, right? And eventually, we are going to we have the analytical solution for this one, right? We are going to compare this 8-panel system to the analytical solution we already have, right? What does it mean? What it means essentially, we are going to get 8 pressure coefficients, right? For 8 points on the cylinder. But we already have the distribution all over the cylinder. If they match up with the distribution we already have, we essentially have a very good result, right? And you do it for 4 panels and then compare the 4-panel results, which will give you only 4 pressure coefficients, right? Because you only have 4 panels. Compare it to the 8 results you already have, and then compare to the analytical solution. They give you a basic understanding of why having more number of data points is going to like help us with the accuracy of a numerical simulation system. Okay. Is there any questions? No. How do you feel about the panel theory? Okay, so we have one so-so, a couple of yeses, and some people don't. Okay, that's good. See. Okay. How do you feel about the concept? Do you understand the concept? Okay, that's good. If you understand the concept, that's the idea. And the reason you need to understand this concept is that the other like analytical theories that we are going to develop in the rest of the course are going to be based on not panel theory per se, but based on the integral method we introduced in the beginning of the class, right? So you have to understand why is this important, what is the velocity induced at the point, or velocity potential induced at the point. All of those things you have to understand that to understand the rest of the class a little better. But the numerical analysis part, as long as you set this system of equations and unknowns, I assume you know how to like find the solutions. And if you don't, that's all right. I'm planning on uploading a YouTube video anyways, so I will try to cover those as part as well. Okay, we have one. Do you want to demonstrate that? Yeah, we have another. Okay, why didn't you say it? Well, you can come here, both of you, and demonstrate. You have it as well. As long as you can rotate it and it can go off, it is the same thing. Let's see what it does. Go ahead, Jacob. Okay. Your lift generation was a little too little. Okay. But I mean, we can say it stayed in air, right? More than you would expect a non-rotating cylinder, but it didn't go up for some reason. You don't have to wait for each other. You can just start throwing this around. Okay, we had a very obvious lift generation. The reason your lift generation was better than Jacob's is you are using plastic cups, which are lighter, yeah? So they need less lift, right, to go up. Yeah. It worked. I mean, I can see the lift generation, but it doesn't go off. Thank you. And let's, Josh, right? Joshua. That was another approach. Actually, I honestly didn't see that one coming. He rotated it in the like, so you move the cylinder in the other direction that I expected. So your flow was in the perpendicular direction to what I expected, right? To what others was. But I mean, you could see the lift generation. Yeah. Yeah. This time it was a little too. It was a little too fast. Okay, thank you guys. I will add your bonus points right away. We have a couple of bonus points. Thank you for your participation. Yeah.